Like sometimes people really need like a lot of remedies. So that's why like this week, today we played a song Remedy. And last time, if you pay attention, it was also a song called Remedy from um, Adele, right? So, like people really, really need a lot of remedies. But most importantly for this lecture, this class, or in terms of performance programming, we want remedies for cache problems. So why cache is a big problem? Because right now we have memory hierarchy to address the huge gap between the processor and memory speed. However, without those remedies that we will introduce, there is no way, or say it's very likely that we are going to waste this additional resources that we have been provided. And regarding cache, we have structured the cache carefully in a way to address the demand of applications in a way that every cache is right now pretty much like a weight associativity cache. So the idea of weight associativity cache is considering that we are building a hardware hash table, but try to remedy the case where we are going to have collisions. So, but because this is done in hardware, so anything fancy that you can do in software, for example, linked list or like some kind of dynamic links, you can dynamic links, you cannot do that, right? So it turns out the only thing we can do is that we make each hash entry with multiple blocks associated with it. And you heard the term associate, right? So that's why each of the hash index will map to an associativity set, right? So what happens is that, okay, right now, if we want to access the cache, we have to know which associativity set that we have to look up for our data. And again, don't forget, when we access cache, your command, your instruction include a memory address that you want to access. And in fact, that's what we want to use to identify which data you are looking for, right? So, or instruction you are looking for. So it's always important to remember when you solve a cache problem after you figure out the cache geometry, memory addresses, right? So then with the memory addresses, I heard some of you were discussing this before the lecture. With those memory addresses, what we really need to do is to partition it. And sometimes, most of the time, and in fact, most of the time in this class, we write this memory addresses into hexadecimal. And there's a reason for that, because hexadecimal is such a great thing that we make each of the bit in binary to be like 4 bits of the binary as a single digit in hexadecimal. So we can save space, make it look better, right? But in fact, when you partition the address, it's still based on a binary. So the last part of the address partition is going to be your block offset. And the idea of block offset is that I want to identify which part in the block may contain my data, right? So then that's why you need the block offset. And because of that, your block offset is related to the size of your block. So, and as with C equal to ABS, you know the block offset is calculated as log block size. And the reason why it's log block size, because like in binary, you want to represent the block offset, you have to use that many bits, right? So the first part, the least significant bits, they are the block offset. And because this is hardware, we don't want very complex hash functions. So turns out the set index, which is the second least significant part of your address, will be used as the set index. And the remaining part are considered as tag. And with that, we use the set index to figure out which associativity set that we should look for the data. And then we compare the tag of each block to figure out if this is the data we want. And again, how many bits are there in each part of the address? We have been talking about this equation C equal to ABS many times, and I'm not that kind of people that I like you guys to memorize a lot of things, but in fact, in computer architecture class, we do not have too many equations for you to remember. And like performance equation and also plus this one, promise you, that's all. These are all three things that you have to remember in terms of equations, right? So based on that, we can pretty much simulate the cache behavior. And we know like for this kind of code, it's completely a miss. So what's going on there is because we have several different sources of miss that's interplaying. So there are three types of misses: compulsory misses, capacity misses, conflict misses. So remember the order I introduced them. The compulsory misses means that it's the first time access of a block. And then capacity misses means that the working set surpass the capacity. So a lot of you still get confused about what is capacity misses. So in fact, some of you, like 2 days ago, I received an email over the weekend saying that I believe I have done everything right. And in terms of that, I found in the student's calculation, it's all about like, okay, there are like 16K elements. So the capacity, the working set should be 16K times 8. The answer is not right, because considering we have the stride, then it's probably not that size that you are touching, right? So it's an evidence that a lot of you still don't get the idea of working set. And again, and the third type of misses is called conflict misses. The conflict misses, they have a strict definition that's not related to the capacity of your cache. So that's why I introduced them in this order. If you want to declare something as conflict misses, you have to say, this is not compulsory miss. This is not capacity miss. Then you can say this is conflict miss. If you didn't prove the priori two are not a cause of misses, you cannot say this is a conflict miss. So that's why a lot of you, when you answer this, like some of you, I think some of the questions are very interesting in a way that, is there a specific format or a specific keyword that I'm looking for in your answer in the autograder? The answer is no, because yes or no, because if the answer is conflict misses, I definitely want you to prove this is not capacity miss or not compulsory miss before you can say this is a conflict miss. So if you don't have these elements, I'm not going to give you grades, because that's not a full proof of this is a conflict miss, right? So this is a summary of the common fallacies that I found regarding the assignment 2 and the cache misses. So first of all, regarding capacity miss, is not related to the size of the complete data structure. It's about the working set size and the cache capacity. So what does that mean? If you have a question you believe is a capacity miss, but the autograder is still giving you the wrong answer, and that means that you probably missed any of the following. So for example, like we said, it's a working set. So you have to define like, okay, the starting address, the end address, and between this range, we have visited this many blocks, right? And if you don't have that discussion, you didn't even touch the concept of working set size at all. How can I give you correct, right? And then The second thing is that, right, like I said, the range, right? So you have to say what's the first address, what's the last address, right? So a lot of people, like I see, like your answer is more about like discussion only. There's not really like a table that being listed, right? Thinking about all the slides that I show you, have I ever discussed the miss rate without showing the table of addresses? Never, right? And why are you trying to do that in your assignment? And then like asking me, why am I getting it wrong? Right? You just don't listen to me. Why should I give you correct? Right? So the thing is that you have to show those addresses. I know it takes time. I know you hate doing this. So that's why I'm telling you, start your assignment as early as possible. Because this assignment, as I told you, it takes many hours to finish. Right? And then you have to count the number of blocks that being touched, because the working set size is about the number of blocks, right? And remember why it has to be number of blocks, because for each cache access is block in, block out, right? And finally, you have to compare the capacity of your cache with your working set size. Like a lot of people, when they send me the answer, they say, well, this is the working set, or this is the total data structure size. They never talk about the cache size. Come on, this is capacity miss, and you don't talk about the cache capacity. How can I give you credits on that, right? So sometimes pay attention to what the autograder tries to tell you, right? If they say you have to discuss cache capacity, that means you have no respect to the capacity miss itself regarding cache size, right? And like conflict misses, right? In fact, I would say if you feel like the answer should be conflict misses, it means that you will take the most amount of time in addressing this. First of all, you have to prove why they are not compulsory misses, right? So if you don't discuss that, you cannot say this is conflict miss. And in fact, so there is a priority in characterizing cache misses. Compulsory misses should always be the very first thing into the discussion, saying that we know this is not a first time access, right? So remember, every block that is visited for first time, it must be compulsory misses, right? So if you cannot prove this is not a compulsory misses, then it has to be compulsory misses. So compulsory misses has to always come first for every this kind of question into discussion. And then you have to discuss capacity. And finally, you can say if it's not either compulsory misses or capacity misses, then you can say this is conflict misses. And even for conflict misses, you have to show, because of this table of addresses, they all map to the same associativity set, so it's conflict. So hopefully that will help you to address all the assignment questions. And again, there is no short answers to each of the cache miss problems. There is no short answers. Like some of them, I counted the number of words that I put has to be 1,000. So like if you haven't started, I really encourage you to start it as soon as possible. All right, so this is a summary from what we learned. But again, I haven't tried this question, first time trying this question, and I'm looking for your innovative answers to this question. Grab a few people around you and let's talk about this. All right. So, what do you guys think? I feel this discussion is more lively than I was envisioned. So it sounds like a lot of you have some good ideas, and we can hear from you guys. So in the future, if you see some of it is starting up a company, you would know if I should join or not, right? If they are good boss or not. Any idea? If your budget limited, this is a really hard question to say, right? What are the potential approach that you would do to maximize your outcome? What do you think?
Focus on the most essential components and fully utilize whatever.
Fully utilize whatever you have. Tell me more about it. Some example.
Um, so if you have a certain amount of memory, I should have computers.
Well, it doesn't have to be computers.
Okay. For my senior design project, I took a motor out of a washing machine,
Mm-hmm.
so that way we don't have to buy a motor.
Mm-hmm.
Use a. I had a washing machine sitting around, didn't work, but the motor works. So,
Mm-hmm.
you know.
Okay, so find some like secondhand parts. Okay, what else? Mm-hmm. 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 Okay, what else? Okay, so those answers are good because that's actually better than I was thinking because I was thinking about like would I hear some random question that's totally unrelated to the lecture today, but fortunately I think we are still on a track. So today we are going to talk about some advanced hardware techniques in improving memory performance, but I have always assumed that you guys read a paper before coming to the lecture. So why don't you guys start with showing me your understanding about the hardware mechanisms that are commonly used. All right, let's take a look regarding what you guys think. Okay, so this is definitely a question we should have some discussion. So why don't you guys talk with each other regarding what you guys think?
if it's a miss, it's a miss. It just would help the it would make a miss less possible. So yes, yeah. So I think three though. You have the thing to eventually do this. So I think three for sure. Two. Yeah. So I think
All right, let's take a look. So now more than half of you think the answer is D, meaning that 3 of them you think would improve the miss rate. So there's one thing that you guys don't agree that would improve that miss rate. What is that? Okay, so like 1, 2, 3, 4. Let's say that one thing together, right? 3, 2, 1. 3, 2, 1. 3, 2, 1. Okay, I hear like 4, I hear 2, right? So that means we definitely need like a whole classroom discussion, right? So first of all, what is non-blocking pipeline multi-bank cache? That's why I want you guys to read a paper, right? What is like a lot of you like you kind of like I know everything, right? But the thing is that sometimes you really need to read the paper before coming to the class, right? So what is non-blocking pipeline multi-bank cache?
The cache is divided into multiple banks so that they can be processed in parallel.
Okay, so the idea of okay, so first of all, let's talk about what is the traditional blocking cache, right? So when you hear the word blocking, right, that pretty much means that when somebody is operating on the cache, there is nothing else you can do, right? And in fact, by nature, that's how memory devices is working, right? Because, and the reason why we have to do that is because think about this, right? There is only one word line should be activated when at the time we are accessing the cache. If you try to access like activate multiple word line, meaning that you are going to access this like 2 blocks in parallel on a single unit, then the result you are getting is becomes something like very weird signal, right? So in the electronic device, you can only allow one word line, which means that one line to be driven when you are accessing. So by default, every cache, every SRAM is blocked. What does that mean? If I am doing a read access to the cache, there should only be one read access going on, right? But as you can imagine, this is not very efficient, right? Because it means that I always have to wait for one block to finish before I can read another block, which is very inefficient, right? So what if, what if I do non-blocking? So the idea of non-blocking cache is not actually making your cache or the lower level memory hierarchy being able to activate 2 word lines in the same time. But in fact, we are subdividing this memory array into multiple different units. And different units, they can perform different access simultaneously, right? So what happened is, as long as I have a cache miss, when I need to access lower level memory hierarchy, as long as these 2 blocks, they are lucky in a way that they belong to different memory array, cache array, I can perform access concurrently, right? But as you can hear, there's no guarantee. You can always perform operations concurrently, but there are chances that you can perform operations concurrently. right? So this kind of approach is called non-blocking cache. Do you think it would improve the miss rate? Do you think it would improve the miss rate? No, because a miss is still a miss, right? It's just making the access more parallelizable, right? A miss is still a miss, right? I just can serve more miss at the same time, right? So what it would help is to reduce the miss penalty or the access time if you put it on L1. But it doesn't help to improve the miss rate at all. If there is a miss, it still has to be a miss. I still have to find it on a lower level memory hierarchy, right? So what is multi-banked cache? So, the problem with non-blocking cache is that you need several different front ends to receive those memory requests, right? So we can say things in this way, right? So think about, I feel like a lot of things are changing. How many of you have been physically visiting a bank recently? Okay, good. So the thing is like, I don't know bank now because I haven't been visiting any bank for quite a while. But traditionally, right, like there are several counters within the same bank, right? And in each bank, but what does that mean is that each of the counter, they need a person to be there, right? So, and what does that mean is that you need several different front end to serve those requests, right? And hiring persons, they are expensive, right? So the problem with that is because it's costing more. So right now, what people would do, right? Like a lot of banks, I observed that they don't have multiple people in a counter, right? Typically, they just have one or very few active counters, right? Everyone has to go through that, right? And well, this is probably not in a bank, but in a Starbucks, right? Like there's only one people doing the check, like doing those like order, right? So once you're done with the order, you are sent to somewhere else, right? So the same thing in a multi-banked access is that there's only one unit still receiving those commands. So what does that mean? At any cycle, you can only receive one memory request. So previously, when we partition them into multiple different units, you can send those commands concurrently. But now with multi-banked, you are not able to send multiple commands at the same time. You can only send one command at the same time. But what does that mean in terms of improving performance is that once I receive that commands, I can distribute those commands, one command to the corresponding unit that I own. And then once I have done that, I'm ready to receive another command and then distribute it to another unit, which we call bank here. So if you pay attention to the timing diagram, previously with blocking single banked design, you can only send one memory request after another. But with multi-banked, pay attention to the timing, right? After I receive the first request, the next cycle, I'm able to receive another request if it goes to a different bank. And then I can receive another one, and if it goes to a different bank, they can perform in parallel, right? And if you have like non-blocking cache with multiple channels, that means that you have multiple units that can accept commands. This 4, they will go parallel. But that's more expensive. That's 4 times expensive. So if you can do this, that's actually saving you a lot of money, but with a slightly better performance than, still a lot better performance than one after another. So is this going to improve the cache miss rate? No, a miss is still a miss, right? So So that's the reason why we are doing this. So in terms of non-blocking pipeline multi-bank cache, it doesn't help improving the miss rate, right? It's simply the miss penalty and bandwidth. So what is early restart? The second one we talk about is the critical word first and early restart. What is that?
When you find what you need, you can immediately start using that while you load the rest of the other things in the background.
Okay, awesome. Right, so remember, we mentioned that for cache access, it always has to be block in, block out. Right, so when you have a cache miss, the traditional way of doing this is you have to get stuff done and then fetch the whole block. So it turns out you can only restart when everything is back, right? So during this whole period of time, your processor cannot do anything, right? However, what does that mean by early restart and critical word first is that as long as I get the word that I want within a block offset, I can immediately respond that word to the processor to let the processor restart so that I can save some time. So again, is this approach improving cache miss rate? Is this improving? No, because a miss is still a miss, right? I'm just letting the miss penalty shorter by responding the word that you want earlier, right? So this is not helping the cache miss rate either, right? So how about prefetching? We learned it. Is it improving the cache miss rate? It could improve sometimes. It could hurt sometimes, right? But things we say would help, right? So I would say, yes, it would help compulsory miss, but it would hurt conflict misses sometimes, right? So be careful about this, but at least to some degree, it could help. How about write buffer? No, why not? What is write buffer?
Combine all the writes together.
Combine all the writes together? Is it a main purpose of a write buffer?
Write first and then let it write back later.
Okay, so here's the thing, right? If you think about the overhead of writes, right? So right now, even though we have critical word first, early restart, you still have to wait for this whole period for data to be written back. Agree? And writing is also very time consuming, right? So the idea of a write buffer is that between two levels of memory hierarchy, I add another buffer. So whenever I have write traffic, I put this into a small SRAM designed cache to serve this write first. And then in the meantime, since I have deal with this written block, I can fetch the new block faster and write back the stuff later when I really need to have the data presented in L2. So that's the concept of write buffer. And in fact, all the buffers that you have heard in system design, they all serve for this kind of purpose, to allow the resumption of operation first to reduce the blocking time of your system, right? So I don't know how many of you are taking operating system right now, but I don't know if they are still reading this paper, but there is a very good paper from Butler Lamson regarding computer system design. Like write buffer is definitely one of the ideas that is great, that should be reused all the time to solve this kind of timing problem, right? And in fact, not only operating system design, not only software system design, hardware also does that, right? So write buffer is actually try to reduce the penalty of like write back. So in this way, is it improving the cache miss rate? No, right? Again, it just make the overhead of write back smaller, right? So, and another thing that potentially write buffer is also good is that sometimes if I'm consecutively writing to a block, and if I'm fortunate enough that the data that I want to update, they could be merged with the content that's currently in the write buffer, then you can achieve the effect of write merge. However, again, it still doesn't help the case of miss rate at all, right? You just make the miss penalty smaller. A miss is still a miss, right? So it turns out, if you review this one, only one of them is improving the cache miss rate. Only one of them is improving the cache miss rate. So I believe the majority picked the answer D, right? So that's another evidence that even though you are able to see other people's monitor, don't see what they are answering. And in fact, one thing I love about Prairie Learn is that every question is randomized. And like we randomize all the numbers, all the options, and like in multiple choice questions, we are allowed to define like 10 different options, and we just show you 4 of them, right? So what does that mean is that everyone is going to have a different set of answers. So you should never trust the one beside you, right? Even though you are able to see that. But here's the thing, right? If we have a summary regarding the hardware mechanism that we have learned from the textbook, only one of them, called prefetching, is going to help compulsory misses, but the other never helps improving the cache miss rate. So if you review what we have learned, right? If we really want to improve the cache miss rate, hardware doesn't really help. Hardware is not the best approach to deal with cache misses. So why don't we try to use programmers to improve the cache miss rate? And in fact, I would argue programmers like us, we are the best group of people to optimize the cache miss rate, because remember, the hardware is designed based on the theory of locality. If we can redesign our software, our algorithm to explore locality better, that's the key to cache-aware, cache-friendly algorithm design. So let's talk about data structures first. So let me show you this. What if I do this? Okay. This is a question with only 2 options. All right, let's take a look. Okay, so a lot of you think the answer is B, some of you think the answer is A. So why don't you guys try to convince each other? You know, sometimes majorities are wrong.
Okay.
All right, let's take a look. So after discussion, okay, more of you go with majority. So, but why? Okay, Kelsey, right?
We were talking about spatial locality.
Spatial locality, okay.
If you have an array of objects, you have to go through find all the ones that are assigned one.
Mm-hmm.
Take the average. Whereas if you have an object of arrays, you just find the one array that's assigned one.
Mm-hmm.
All together.
Okay, so if you pay attention to, but let's look at the demo first, right? So first of all, like some of you might be thinking about, would that really make a difference, right? So okay, so here's the demo. First of all, the left-hand side is the array of objects and object of arrays. So if you're not familiar with C, so what's the difference between this? So the left-hand side is the it's each of the we abstract each of the record as a single object. So that's why we are creating array of objects. So for each of the So for each of the array, sorry. So for each of the array object is representing a student's record, right? And for the other side, we are doing object of arrays. So what does that mean is that if you see this like pointer, right, in C, each pointer is essentially meaning consecutive, like it could be used for a memory address. And typically you are declaring this because you want to allocate some consecutive locations later, right? And if you have a double pointer, that means that you are trying to allocate a two-dimensional array. So what we are doing is that we are trying to create a table with an array of IDs and a table of homework elements. And we have an array of average, and we want to fill in those averages, right? So if you pay attention to the code that we have to perform the specific queries that we need to achieve for the feature that we want to count the average of each homework element. For the left-hand side, the array of objects, what we need to do is that we have to go through each object, specifically pick the homework element, and then put that result in an accumulator, and then find the average. And for this one, we go to that specific column in a table, or if you can store them in a transposed order, right? You are going to each specific row, and each specific row is basically a column, right? So all you need to do is traverse that logically column, physically row in a table to count the average, right? So if we could have done that, right, what's the performance difference? So now I'm doing this, and assuming this is approximately the amount of students at UCR, and this is, let's say that each of you have like 10,000 elements for this program to count. So if you do an array of objects, which looks more elegant from the software engineering perspective, you will need 8.5 seconds. However, if you do it in object of arrays, that's only 3.6 seconds, right? And why is that? If you look at how it locates on the memory, if you do array of objects, it's pretty much like I'm only visiting homework, and then I'm going to another block of data that contains the homework, right? So you can imagine the utilization of this block is very low, right? I just fetch the block, I pick one word from the block, and then I don't need anything else, right? So you are basically suffering a lot of misses. What type of misses do you think we are going to suffer from the behavior of the code? How many misses? What kind of misses is the majority type of misses here? Compulsory misses, right? Like if I only use the data structure for just once, right? Every time when I fetch a homework item, it's pretty much a compulsory miss. However, if I can do the column store, what happened is that since each column is right now physically located together, when I perform the access, right, it's all sequential. So you can highly utilize the spatial locality to get better cache miss rate. So a lot of people, they have the misunderstanding. They think the database is exactly like the Excel spreadsheet that I would create when I store the data. However, like computer architects like us, we work together with the database system guys. And I do want to say, like, database system has a lot of performance we have to tune, right? I also published quite a few papers in database realm because like a lot of optimization we have to do in database. So like a lot of people, they might think this is the way how I store the records. Like each element, like each index associated with a record, they should be stored consecutively. However, in fact, for this data you see in our database systems, we actually do column store. What does that mean is that for each of the elements, I would store a tuple like this, like their data value and the index associated with that record. And then the next element in the column and then the index associated with that, instead of storing it in a row order. Right. So most of the database tables, they are designed to be column stored because most of the time, think about what kind of queries are we going to perform. Most of the time, you are going to like perform queries like select a few columns with the column criteria fit for a certain conditions, right? So both when you are comparing, when you are selecting, it's column-based, right? So why not making your storage column stored? right? So that's why in database system, most of them are column stored because based on the behavior, how we use those SQL queries, column store works better. I mean, you can always find a case that the row store doing better, but remember, when we optimize, we are optimizing for the most frequently used cases rather than those rarely used cases. And don't argue that with me, but statistically, more SQL queries are column store friendly rather than row store friendly. So the first trick I would say, right, when you change the data layout, it would potentially facilitate the all three type of misses, right? Like switching from row store to column store, if you only use this column for once, you will definitely improve the compulsory misses because there are fewer cache blocks you have to use to get the column content. However, if you are going to use this column for many times, and if this is a really large column, you are going to reduce the COCO capacity that we need for this access, right? So you can reduce the capacity misses. If this is not such a large column, but if you make them consecutive, you can also reduce the chances of them being conflict in associativity sets. So that's why when you rearrange your data, you are going to help on all three type of misses. So first of all, right, if you are meeting a cache problem, right, I didn't say data structures are unimportant. In fact, you have to think about, am I designing my data structure correctly? Right? Is it friendly to the cache access? Now, the second type of optimization that we want to talk about is how can we structure our loop in a better way, right? In fact, it's hard to imagine that you don't have loop in your code, right? And one of the most significant example that we have been seeing is this, right? Like previously, we have been mentioning if you can change the order of traversing the loop, it will significantly reduce the CPI, right? But now, this is the time to talk about the answer, right? Can you guys tell me what's the answer? Why is it improving the cache miss rate? What kind of misses are we improving? Okay, so for this example, is it compulsory misses? Are we going to see different numbers of compulsory misses? Be careful, be careful. Are we going to see different numbers of compulsory misses? How many compulsory misses are we going to see? What's the definition of compulsory misses? Kelsey?
On an empty cache.
Empty cache line, or what's the other name of compulsory miss? The first time accessing the element, the cache block. The first time accessing a cache block. Are we going to see different numbers of cache blocks being visited? Yes? Are we seeing different number of cache blocks being accessed here?
In the second one, every time you access, it's in a different cache block. So every time you're accessing a different.
But are they physically the same block?
Yes.
So the second time I visit that block, is it compulsory miss? It's being kicked out, right? So it's not compulsory misses. Is it capacity misses? Would this kind of access be gone if, like saying that if my data is smaller, is it has to be capacity misses?
The data is smaller than normal, I guess.
Then what type of misses is that? It's conflict misses, right? So if you do loop interchange, it's going to help you. So this mechanism is called loop interchange. As its name, I'm changing the order of accessing the loop, right? It's help to, if you have a really large data structure, you can reduce the capacity misses because between 2 points of observations, you are going to visit fewer number of blocks, right? So that's why it helps to improve the capacity misses if you have a really large data structure. However, if you think carefully, right, even though my code has a really small size, this is still going to be there. And the reason is because you are going to create a lot of conflict misses as well, right? So what does that mean is the loop interchange would help on both. Now let's take a look at this. So previously we mentioned for this kind of code, we have to use a hardware optimization code. What kind of cache? No, well, you can increase the weight associativity, but for Noam Joby, what did he say? Like for Noam Joby's paper, what kind of mechanism we could help to improve the cache miss rate for this one? Victim cache, right? But is there a more innovative way we can make this code has fewer cache misses, right? Let's look at this example. What do you think? Oops. Oops. All right, let's take a look. Okay, so I love this figure because it means that we need discussion. So why don't you guys go ahead, discuss with your friends, what's the cache miss rate now? All right, let's take a look. After discussion, okay, more of you think the answer is A. Some of you still think the answer is C. So first of all, let's try to run a demo. And let's see if the demo would give us some more insights about this. So first of all, like loop fission, this is the mechanism that we are talking about. So the idea of loop fission is that this is the original code, right? And this is probably the code that you guys like to write most of the time because it's elegant. One iteration, one loop, and it says like EI equal to AI times BI plus CI divided by DI, right? And the other version that we demonstrated is actually, instead of one loop, I separate them into two different loops. And this loop has two parts. The first part, I only perform everything before this division and store it in EI. And finally, I divide each EI element with the DI, with the second loop. This two should generate the same result. Do you all agree with that? Yes, right? Okay, so, but what about their cache behavior? So now, let me run this demo real quick with Valgrind, right? So now, as you can see, right, with version A, we have 100% miss rate in the loop. With version B, you see the cache misses are significantly reduced, right? So that means it's a very effective way to reduce the miss rate. And but what is the miss rate? What is the miss rate? Can we do a numerical analysis on this one? So first of all, whenever we ask you about miss rate, what are the parameters that you need to get regarding the miss rate? Okay, well, let's get this done, right? Let's assume that we have done all the cache simulation. What do we need? What are the two things that you need to calculate the cache miss rate? Total memory accesses and the number of cache misses, right? So what's the total number of cache accesses or memory accesses here? How many memory accesses do we have to perform? 512 times 6 in total, right? Because here we have the first loop, we have 512 iterations. Each iteration has 4 accesses. In the second loop, we have 512 iterations. Each loop has like two memory accesses. So it's a total of 3K. How about the number of cache misses? What kind of cache misses are we still going to see? Compulsory misses. So how many total compulsory misses are we still going to have? For the first loop, how many of them? Why do we have to divide it by 8? Okay, because each block we have 8 elements in total, right? How do we know it's 8 elements? Because each double is 8 byte. Each block is 64 byte block, right? So each block contains 8 doubles, right? And the first access to each block is always a compulsory misses. However, why don't we have other misses? Why don't we have other misses? Like by rewriting this kind of a code, what kind of misses are we getting rid of? Conflict misses, right? So it turns out there's only compulsory misses remaining. And fortunately, when we access the second loop, right, the EIs are still there, right? So we can say, well, there's a total of 320 compulsory misses in total. So doing that, what's the average cache miss rate look like? About 10%, right? So we are actually making the cache miss rate go down from 100 to just 10, a 10-fold improvement, right? So sometimes, right, if you see people splitting the loop, it seems stupid, but there could be a reason for that, right? Okay, so if you can tailor your software in this way, the NVIDIA processor doesn't need victim cache anymore, right? So the answer is A, 10%. And this kind of mechanism is called loop fission. Basically, it means that we are split up a single loop into 2 to remove the conflict misses. So this is really useful when you have limited weight associativity on your cache. So, but the same mechanism, if I am giving you an Intel processor, is it going to be useful or not? Is it going to be good or bad? All right, let's take a look. Okay, so this is a good question that we need to discuss with each other. So why don't you guys try to discuss with each other? All right, let's take a look. After discussion, okay, more of you think the answer is D now. So again, we want to see the demo, right? So let's try to run this on Intel processor. So again, the same pieces of code, but you know, for like Intel processors, we have performance counter that would help. So why don't we just like run this, like recompile these pieces of code. Oops, let me do this and see on Intel processors, how do they perform? So if I run this on Intel processors, look, if I do loop fusion, the instruction count is significantly lower than loop fission because I have just one single loop, fewer control overhead, and also fewer number of memory accesses, right? So if you look at the number of memory access in the top is this, and the number of memory accesses for the loop fission is this, right? The cache miss rate, they are all about the same because both of them you are going to see compulsory misses only, right? And the second loop fission, it does have lower miss rate just because you have more cache accesses, right? So that amortizes the total amount of miss rate. But if you look at the execution time, loop fission is going to make it slower. And again, a lot of people, when we do optimization, we think, well, we optimize for CPI. We optimize for cache miss rate. But don't forget, performance is about three factors: instruction count, CPI, and cycle time. On the same processor, if you cannot improve the CPI significantly, but increasing the instruction count, you are going to hurt performance anyway, right? So what does that mean? Is that for Intel processors, or in general, any processor with rich weight associativity, you should actually combine data access into the same loop. So this approach is called loop fusion. So for loop fusion, you can reduce capacity misses, or because you are actually making and reduce the number of memory accesses in general, right? Because you are compacting your accesses, right? So, but how do I know which way should I program? You really have to know what kind of processors that you are dealing with. So sometimes a lot of people would say, why compiler doesn't do this for me? The answer is that an x86 code will run on AMD processor and Intel processors. They have different way associativity. I cannot assume this is the processor you are going to run, right? So compiler typically won't do this automatically for you, right? So what does that mean is that as a programmer, you have to know more about your code. And now the next question, can you answer this question for me? All right, let's take a look. Okay, most of you think the answer is C. So why don't you talk to each other regarding why do you think it's C? All right, let's take a look. After discussion, okay, 75% of you think it's C. You know, like let's see a demo first. Okay, so for this is the left-hand side, right? The data structure that we have, right? So why don't we just try to run these pieces of code? So here I do have this one, right, showing the size of it. What's the output here? 40. So a lot of you think it's 32. You think, seriously, like you asked me this question? Are you challenging my understanding of CS201? And I'm telling you, you are wrong. This is 40. But why? Why is it 40? So if you so here's the thing, right? So for so a lot of us just think about like what's the total number of bytes that really needs, but forget about architecture. So in fact, in computer architecture, every instruction, first of all, they use byte addressing to access the memory locations. However, there is a requirement for data access instructions is that the memory address that we use for each instruction, if this is an instruction that accesses 4 bytes, for example, if you want to load an integer, if you want to load a floating point, that particular memory address must be able to divide it by 4. And if this is an address that is accessing 8 bytes of data elements, that memory addresses needs to be divided by 8. This is from the circuit design perspective. Because if you don't do this, then it will be split into 2 different instructions when you load an 8 byte and you need another instruction to pick specific bytes. So if you look at the layout, the first elements here, ID start with 0. That's fine, right? And then after I use 4 bytes, is 4 divided by 8? Can 4 be divided by 8? It's not a multiply by 8, right? So then turns out you have to find the next address that could be divided by 8. So instead of starting at 4, it has to be starting with 8 because the next one is a pointer. Every pointer occupies 64-bit. So for the next integer, it starts with this location 16, fine. However, similarly for this double, it has to start with 24 instead of 20 because 20 cannot be divided by 8, right? So turns out it would take 40, right? So if I really want to improve the usage of memory, you should move the partition next to the ID, right? So if we run a demo again with, let me see, with another version that I wrote, like if I could modify, wait, memory usage A, memory usage B. Okay, if I could modify the data structure in a way to reorder this like ID and the participation, then I would be able to get 32 instead of 40. So again, data layout affect the total capacity of your structure. So you have to be really careful about, sometimes I'm just like picking those like order randomly, but the order matters. Okay, before you leave the classroom, several things. We still have reading quiz 5 due next Tuesday. Assignment 2 release this Thursday. And as I said, it's not as simple as you could imagine. And midterm is exactly the same environment and reservation system as the practice exam. You've already mixed the practice exam. Sorry, you don't have any chance anymore. And you can start making reservation on or after this Thursday. And first come, first serve, you have limited slots. And if you cannot reserve any slots that you can attend that exam, it's your responsibility, and you're not going to get credits if you didn't take the exam. And both versions would include the lectures on this Thursday. In fact, this Thursday, I will going to give you a lecture that my favorite one throughout this quarter. So I would definitely test a lot on that one. And if you can get an early slot, because the reason why I have to do that is because typically, if we do the exam in person, it has to be that specific day. And for the testing center, they cannot let us saying that everyone take the exam at that specific day. They say, we always have to reserve 1 week slot. But the problem with 1 week slot is that even though we try to randomize the question, some people will try to leak those information to the later student. So and the student who take the exam later is going to have more advantage because they hear more, they can know like what may be covered. So I don't think that's pretty fair to the student who take the exam early. So what I'm going to do is, if you take the exam on Monday and Tuesday, I'm not going to test you on the materials on the lecture on Tuesday. However, if you decided to do the exam later, I cannot prevent you from doing that. However, I'm going to give you a different set of questions, and it will cover the lecture on Tuesday, next Tuesday as well. All right, so other than that, enjoy the rest of the day. I will see you on Thursday.